Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, we'll continue talking about A star this lecture. We started to study it last lecture, and we said that A star will expand the node with the least total cost. And with the total cost, we mean the sum of the backward cost, which is the actual cost between going from the start state to the goal state, plus the estimated goal going from the current state. The actual cost is from the start state to the current state, and the forward cost is the estimated cost going from the current state to the goal state. And I think we stopped at that question, whether A star is optimal or not. And let's look at this example to see if it is actually optimal or not. So if I want to solve this problem, we'll start, of course, with the start state. Let me do it here. So the start state, okay. What will be the cost of the start state? It's the backward cost for the start state is 0, and the forward cost is the estimated value, which is 7. So the total is 7. And of course, we'll expand it to the state A and the state G. Now, what is the goal? What is the cost of the state A? The cost of state A is the backward cost plus the forward cost. The backward cost for A is 1, because the actual cost from the start state to A is 1, plus 6, because 6 is the estimated cost from A to the goal state. So the cost here will be again 7. How about G? The backward cost for G is not 3, it is 1 plus 3, because going from the start state, we have to go to through this path, which is S to A to G in this case. Okay. Sorry, this G, not this G. So this going from S to G, the backward cost is 5. Going from S, the backward cost is 5, plus the forward cost, which is 0. So the total cost is 5. Okay, now we have in the fringe two nodes, A with the cost 7 and G with the cost 5. So we will get G out of the fringe, and we declare that this is a solution going from S to G. Now, is that the optimal solution? Of course not. The optimal solution in this case should be S to, sorry, I don't see the, it's S going this way is the optimal solution. S to A to G. Because the total cost for this solution is 4. Okay, so that's the optimal solution. That means that A star in this case didn't get the optimal solution, which means that A star generally is not optimal. Type. What went wrong here? What prevented us from getting the optimal solution? The answer simply is that we had this case, which is the actual goal is less than the estimated goal. Where that happened? Actually, it happened here, for example. We estimated that the cost from S to G is 7, but actually it's 5. Okay? And here we estimated the cost going from A to G to be 6, but actually it is 3. Okay? So when we have this condition, that might delay the optimal solution. Okay, and thus you might not get the optimal solution. Delay means it will estimate a higher cost than it should be, which means that it might stay for some time in the fringe without being expanded. Okay, so we need estimates to be less than the actual costs, not more than the actual cost, which means that we need estimates to be optimistic, or we need estimation of the actual cost. Okay, if we do that, then the optimal solution will not be delayed on the fringe, and eventually will be expanded. Okay, so that leads us to what we call admissible heuristic. Admissible heuristic. Okay, so admissible heuristic is an optimistic heuristic, which means that it will always estimate the cost to be less than the actual cost, which will give a chance for the path of the optimal solution to be expanded in from the fringe. Okay, of course, in comparison to the inadmissible heuristic, which is a pessimistic heuristic, which assumes that the estimated, which will give us an estimated cost that is higher than the actual cost. So our focus will be on admissible heuristics, and let me define it more formally here. So H is an admissible function, which means optimistic, if the estimated cost for every node, for every state in the state space, the estimated cost going from that state to the goal state will be less than or equal to the actual cost, the true cost going from that state to the nearest goal. Okay, so that's why we call it optimistic, because always the estimations that we will get will be underestimations. We think that we can go from that node to the other node, to the goal state, from that state to the goal state with cost of 15. But in reality, it is 27. If that's the case for every state, then this heuristic is optimistic, or in other words, admissible. Okay, examples. Here is the pathing problem going from the from this state to that state. Let me change this pen. So going from that state to that state, this is the pathing problem. Now we said that we used before Manhattan distance. Okay, Manhattan distance. Now, is Manhattan distance admissible? Okay, let's think together. The definition of an admissible heuristic says that the estimated cost has to be always less than or equal to the actual cost. Is it the case here for every state? Can we say that Manhattan distance in this case admissible or not? Any answers? Saad? It is equal to the exact? Why do you think it is always, Manhattan distance in this case is always equal to the exact cost? Yes. So with the walls, it can be, of course, in some cases, but generally it is equal to or less than the actual cost, because we cannot get better than this. We can have more cost than that if we have walls. If we don't have walls, then we will get into the goal state with this cost. So that Manhattan distance cost will always be less than or equal to the actual cost. Although we don't know the actual cost for every state, okay? But by reasoning, it is clear that because there are walls and we assume that there are no walls, then at least the cost from any state to the goal state will be Manhattan distance between that state and the goal state. Okay, so this is admissible. Another example of admissible function is the heuristic function that we talked about last time for pancake flipping problem. We said that the heuristic function will be the ID of the largest misplaced pancake, which is 4 in this case. Okay, طيب. Why is this admissible function? This says that the cost for this to go from this state to the goal state is 4. Okay, now this is admissible because that's the least cost we can have to reach to the goal state. Why is that? Because to put this one into its position, we have to put the handle here. We have to flip all. At some point, we have to put the handle at that position. Okay, to change this one to this one eventually. Okay, so the cost of this action will be 4. Of course, we might not do it in one step. So that's why it is optimistic, and that's why the estimated cost here will be the minimum cost needed, okay, which is 4. So that's why it is admissible, because the estimate will always be at least the actual cost. In some of the states, of course, it will be maybe the exact cost, but in most of the cases, or generally, it will be less than the actual cost. Whenever the heuristic gives us an underestimation or an estimation that is less than or equal to the actual cost for every state, this is called admissible function. Okay, and coming up with admissible heuristic or admissible function is the actually the art of using A star, is the main component or main step that we will that we will spend time in solving any problem using A star, is to find a good heuristic function that is admissible. And why is that? Because A star, why we should search for admissible function, because it's proved that A star will be optimal if H is admissible. So if we found an admissible function for the search problem, then A star, applying A star using this admissible function or using this heuristic function is guaranteed to give us the optimal solution. Okay, so I hope that this is clear. Now, if we compare uniform cost search with A star, uniform cost search is not aware of where the goal is and tries in many directions. A star with admissible function, it knows where the direction is, and eventually you will find the optimal solution with much less cost than, or much less time than, uniform cost search. Okay, again, uniform cost search will go into many directions, like in this circle, but A star will mess around a bit, okay, explore some of the paths around, but eventually you will go to into the direction of the goal. Let me show you some demos here. Here is a let me change this. I think I have to. Okay, let me show you a demo here before we start. Here is the easy problem going from that position to that position without any walls or deep water or anything. So here is what uniform cost search will do. I think we saw it before, but let me do it another time. Okay, so that's uniform cost search. It went through so many directions, in all directions. It doesn't know that the goal is to the right. That's why it started to search everywhere. Okay, and the dots here are the nodes that were expanded, or the states that were expanded out of the fringe. Now let's see what greedy algorithm will do here. The greedy algorithm will have a heuristic function, and here the heuristic function is the optimal function, which is the Euclidean distance. Okay, so the greedy algorithm will behave as follows. It's optimal. It's very fast. It's easy problem. It's very fast. Went through the optimal solution directly. Now, if we use the same heuristic function with A star, we would get exactly this optimal solution. Now, to make it a bit harder for A star, we will assume a heuristic function that halves the Euclidean distance, okay, between the current node and the goal. So you will see that it's not as fast as the greedy. It starts to search around and eventually actually it doubles. The heuristic is a double of the Euclidean distance. Sorry, it's double. So it messes around a bit, okay, but eventually found, of course, the optimal solution. It's half. Sorry, it cannot be double. It's half the actual cost, okay, because if it's actual cost, it will find directly the optimal solution. This is half the actual cost, so it took some time going around until it reaches the goal eventually. Here is a more difficult maze for A star, which we saw it before. So Pac-Man wants to go from here to there. The dark blocks are states that are visited more than one time, and the lighter ones are the ones that were visited less. So let me do it again. So you'll see that here Pac-Man found the optimal solution. We are doing A star here, but it messes around a bit until it reaches the optimal solution. In comparison to the greedy and uniform cost search went everywhere. We saw that last time, okay, and eventually found the optimal solution, which is going that way, but after exploring the whole space. Greedy didn't find the optimal solution. It was fast, but eventually got a suboptimal solution. A star spent a bit more time than greedy algorithm, but eventually found the optimal solution. A star in reality is used in so many applications: video games, routing, language analysis, machine translation, speech recognition. So many applications use A star. The main art here, or the main step that really needs thinking, is finding an admissible function for the given problem. And as you saw, the admissible function depends on the problem. So we'll have to find one for every new problem that we face. Here is a demo that shows you the difference in time between uniform cost search and A star again. So let me run this. We'll start with uniform cost search. And down here is the number of expanded nodes. You see that Pac-Man eventually found the optimal solution, but if you look here, you will find that the number of nodes expanded is more than 9,000. More than 9,000. Now let's compare that with A star. Let's see what A star, how many nodes A star will do using I think Manhattan distance here as a heuristic function. So you will see that if we go back a bit, you will see that the number of expanded nodes is 182. Okay, compare that with 9,000, more than 9,000 in the case of uniform cost search. Okay, before we go into this quiz, let me see if you have any questions up to that point. Any questions? Okay, good. Let's do this quiz. Now we have 5 strategies that we started before: BFS, DFS, uniform cost search, greedy, and A star. I will show you 5 demos and tell me which is which. Okay? Raise your hand if you know any one of these. So here's the first one. So again, sorry. Okay, so you see the slide now, I think, yes. So let me do it again. So this is the deep versus shallow water. So the deep water here means the cost is higher than the shallow one. Okay, and I want to go from this position to that position. So let's see what is the strategy that we will have in the beginning. Okay, here's the first one. So let me show it again. Okay, which one is this? Random? Uniform cost search. Why do you think so? Let me show it again. Let me show it again. Okay. See if there is a pattern in expansion or not, Ghanem. Is there a pattern, specific pattern here? Yeah, but there is a pattern here. Okay. And also, did it find? Yani, there are two things here. There is a pattern going into kind of levels, and also, if it's uniform cost search, it would have found the optimal solution. Is that the optimal solution, Ghanem? No. Yeah, so for sure this is not uniform cost search. So let me ask another one. Thanks, Ghanem. Yusuf? Yusuf? This is BFS. Yes, why? It's not just in all directions, because we see others also going into many directions, but this one, it was in just in levels, in tiers. Okay. Yes, it's as because it's going through the tiers in the tree, so it expands in levels. As we said earlier, it's like throwing a stone in the lake. You see the waves. So this is BFS. Okay, thanks, Yusuf. Let's go through the second one. Okay, let me show it again. Okay, what is this? Faisal? Yes, and it also explored many directions, okay, because it doesn't know where the goal is, but eventually found the optimal solution. So this is uniform cost search. Thanks, Faisal. Let me show you the third one. What's this? Okay, show it again. Let me show it again. Oops. Did you see it? Show it one more time. Okay, so here is it. Okay, so Saad, didn't hear you, sorry. Say it again. Greedy. Yes, that's a greedy approach. Why is that? Yes, it's expanding the closest one according to the heuristic, and it just went through the very fast, of course, but it's not the optimal solution. Okay, now let me show another one. What's this? Let me show it again. Okay, seems clear to me. Yusuf again. DFS. Okay, why is it DFS? Deep. Yeah, no, it's not from left to right, Yusuf. You mean in terms of the problem? Yes, but it's in the tree. It's going deep. Okay, so going deep, it actually traces the entire space, going through all the possible positions until it found eventually the goal. So that's DFS. The snake. Okay. You cannot. I cannot call it that way because it's not always the snake algorithm, Yusuf. Okay. Let me show you the last one. So what is this one? Let me show again. So which one is this? Anyone other than Yusuf? Okay, Ridwan. A star. Okay, why is that? Okay, and eventually found the optimal goal. Okay, of course, after trying a bit of time in the shallow water, in the deep water, but it get out of that and found the optimal solution eventually. Okay, thanks, Ridwan. Okay, any question before we switch to the new slides? So is it clear how A star is different from greedy algorithm and uniform cost search? Okay, so next we will talk more about heuristics and how we can find admissible heuristics, and then eventually inshallah we'll talk about graph search. I don't think we'll have time today, I hope, maybe, but if not, then inshallah we'll talk about it next time. So we'll start with heuristics. So creating, as I said earlier, creating admissible heuristics is the hardest step in solving search problems using A star. Coming up with an admissible heuristic will be the main problem. And let me show you one way of getting into or finding an admissible heuristic is to find a relaxed problem from the real problem. Let me show you that on an example. Here's the example that we saw many times before, which is traveling from Arad to Bucharest. The real problem states that we have to go through these roads, right? Now, let me relax this problem and assumes that there are new actions. And this is one way, by the way, of relaxing the problem is by adding new actions that are not available in the real problem, but we will assume that they are available in the relaxed problem. So the new action is to go directly, not through these roads, maybe via direct flight, or a straight line somehow, from any state to Bucharest. Okay? So in this case, what will be the optimal solution? The optimal solution going from any state to Bucharest is to go through this straight line. So the distance between Arad to Bucharest, or the cost of going from Arad to Bucharest, will be 366, which is the Euclidean distance between the two cities. Now, this is an optimal solution for the relaxed problem. Now, since this is a relaxed problem with respect to the original problem, then this optimal solution is considered an admissible heuristic to the original problem. Why is that? Because the cost here will be optimistic, because we relaxed the problem. We added new actions that were not available in the original problem. So the cost here will be optimistic, because in the original problem, we will need at least that cost. In most cases, we will need more or that cost, which means that this now is an admissible heuristic with respect to the original problem. So in summary, if I have a problem and I want to find an admissible heuristic for that problem to be used with A star, one way is to think about a relaxed problem from the current problem, and then think of solving this relaxed problem. In most cases, you will find a very easy solution. Actually, you will find the optimal solution, because you can add new actions that will make it much easier. Relaxed means easier. You can think of it that way. So in the relaxed problem, you will find the optimal solution easily. Now this optimal solution is an admissible heuristic for the original problem. Here's another example. The pathing problem from this position to that position. Now, what is the relaxed problem here for that problem? The relaxed problem here is that we can remove the walls, which means that Pac-Man can go through the walls. So that's a new action. if we assume that this action is valid, then Manhattan distance will be the optimal solution. Yani, imagine that there are no walls, then of course the optimal solution clearly will be Manhattan distance. The cost of the optimal solution always will be Manhattan distance. That means that this cost, which is Manhattan distance, is admissible heuristic, or is an estimate from an admissible heuristic to or in the original problem, because we relaxed the problem into a problem where there are no walls. طيب, how about Euclidean distance? Can we think of Euclidean distance as a solution to a relaxed problem? What could be the relaxed problem in this case? So for Manhattan distance, we said that the relaxed problem is that we assume that there are no walls, or in other words, we assume that there is a new action which is going through the walls. Now I can relax the problem more and think of other ways of admissible function, which will be Euclidean distance eventually. What could be a more relaxed problem than what we already mentioned? Mustafa? Yes? Yes, exactly. So we'll assume that a new action is to go diagonally, but plus also going through the walls again, right, Mustafa? Yes, so there are two assumptions here that we relaxed. Okay, we can go through the walls, or there are no walls, in other words, and we can go diagonally. Okay, so in this case, the optimal solution will be, or the cost of the optimal solution will be Euclidean distance. So that's again, it will be again also an admissible function. Which one is better? I think we will answer this later, inshallah. Okay, but generally, the admissible function coming from a more relaxed problem will not be better. Okay, because there are many. We made the problem much easier. Okay, as we have a relaxed problem that is closer to the real problem, the heuristic function will be better. We'll find the optimal solution easier or faster in this case. Okay, now let's move on to another example, which is the 8 puzzle. I think many of you, if not all, are familiar with this. I personally played with it many times when I was a child. Here we have the tiles, okay, with numbers, starting from any state like that. We have one empty spot, and I want to move the tiles around, of course, using this empty spot to go to the goal state, which is having the numbers in that order. Okay, so this is a search problem. Forget about the questions here. This is a search problem. I want to, I will put it that way. Okay, there is a start state, which is this state. There is a goal state, which is this state, and the successor function will always take me, the actions will be just moving one tile around, right? And what else in the search problem? We have the states, we have the successor function, we have the start state, and we have the goal state. So that's a search problem now. Okay, so the states, of course, will be the positions of the numbers in the game board. Now, how many states we have? How many states we have? Saad? Yes. 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 Yes, so it will be 9 times 8 times 7 times 6 and so on until 1. So this is 9 factorial. Okay, so that's the number of states. Now, what are the actions? Already we saw, we said that, which is the moving one tile into the moving one tile from the neighboring state of the empty spot to the empty spot. So these are the actions. Now, how many successors from the start state in this case? How many successor states from the start state? With one. Okay, so it's not an answer to my question. It's a question about the previous one. Okay, so let me say it again. So we said that how many possible numbers we can put in order to count the states. How many possible numbers we can put in this first spot? We have 8 numbers, and we also have the empty spot, right? So we have 9 possibilities to be in that position, right, Ridwan? Okay, now assuming that we already have 1 here, for the second position we have 8 possibilities now, because we already have 1 in the previous one. So we have 8 possibilities in the second position. We have 7 possibilities for the third position, and so on. So it should be 9 times 8 times 7 times 6 until we reach 1. Okay. Okay, the next one, what should be, actually we didn't answer this one. How many successors from the start state? Any answers? From that start state, how many successors we have? Yusuf? Why? Yes, so we can slide 2 or 5 or 3 or 6 to the empty spot. So we have 4 successors. Now, what should be the cost? Any idea? What should be the cost of every action? We are moving just 1 tile, right? So naturally the cost can be 1. We're just moving 1 tile, so all the actions have the same cost, which would be 1 in this case. Okay, so that's just defining the problem as a search problem. Okay, now I hope that you are convinced that this is a search problem. We can solve it with, as we said, any search problem with the interface that we defined can be solved with A star. To solve it with A star, we need a heuristic. Can we think of a heuristic for that problem? Any ideas? What could be a heuristic function here? Yusuf? How far? Okay, you said 2 things here. Let me take one by one. Okay, so you said how far each tile now from its final position, right? This is, I think, what you meant. Okay, how can we get this distance? Can we use Manhattan distance also? Yes, but remember, the heuristic function doesn't have to be accurate, doesn't have to be perfect, right? It just has to be admissible. So we will think about this next, but let's think of it. So what you suggested, I think, can be done using Manhattan distance, right? Okay. So again, the heuristic function that you suggested is the Manhattan distance for, of course, the total Manhattan distance for each tile, going from the start state, or given any state, of course, going from the position of that tile currently to the correct position in the goal state. Okay? Type. Thanks, Yusuf. Now, is this function admissible? if we assume that we will use Manhattan distance? Faisal? Why? Yes, yes. So it will always be the minimum cost, right? To move every tile, because we will have to at least to move it that number of steps in order to get into the correct position, right? Okay. Yes, or in other words, we can say that we discard the other tiles. Yes, in moving one of the tiles, we discard the other tiles. So this is relaxation, right? So this is relaxing the original problem to another problem where we just ignore where the other tiles are and we just move the tile from its position to the correct position. Okay, so this is, again, as we mentioned in the previous, I think, 1 or 2 slides, in order to get an admissible function, think of relaxing the problem by adding new actions, okay, and finding the optimal solution in the new relaxed problem, which is Manhattan distance here. If we move the tiles freely, will give us an admissible heuristic function. So this is an admissible heuristic function in this case. Now, going back to what I think Yusuf suggested. Yusuf, you suggested another one. Yes. Yes. So now this heuristic function is you said how many tiles are misplaced, right? Like what is the intuition here? So this is like one cost of one for every tile that is out of place, right? So that means that I need to move it at least once. I need to move any tile that is not in the right place now. I have to move it once, okay? Or the cost will be at least one, right? Because I have to move it anyway from that position. Okay, so that's a heuristic. Now, is it admissible or not, Yusuf? Okay, in order to help you help yourself thinking whether it's admissible or not, think of a relaxed problem. Is that did you do any relax? Yeah. Mm-hmm. Okay. But one here, let's do it in an actual case. So here is one, and it should be here. So it should be instead of this two. So if we assume that the estimated cost now is one, that means that I will take this tile and put it directly into the correct position. I don't have, yeah, I don't, yes, yes, we don't have to do anything other than just moving the tile and putting it in the correct position. It's like adding a new action, which is you can do any movement of tiles at from anywhere to anywhere. Okay, so that's a relaxed problem, and thus now this heuristic function is admissible. Okay, let's go through this one by one, exactly like what we mentioned. So the first heuristic here is the number of tiles misplaced. We already answered this. It is admissible. Now, just to make sure that you understood this heuristic, what is the estimated cost in case of this start state? If you look at this start state, if we assume that the heuristic is the number of tiles misplaced, which is the second one that Yusuf suggested, what will be the estimated cost here? Any okay, I saw 8, I saw 9. Okay, so let's see. 7 is incorrect, 2 incorrect, 4 incorrect. How can I know? I look at I'm looking at the goal state here. 5 is incorrect, 6 is incorrect. 8, 3, 1, all of them are incorrect. So the cost is 8. Okay, so the cost here is 8. Now, in order to show you a comparison in terms of how fast uniform cost search and A star using this heuristic, okay, using this heuristic, let's assume that we have a problem where this problem, the puzzle problem, we can reach from the start state to the goal state in 4 steps optimally. Okay, so for this problem, which should be easier than going into 8 steps or 12 steps, uniform cost search needed 112 expansion of nodes. So 112 nodes were expanded until uniform cost search found this optimal solution. A star found needed to expand only 13. Okay, so huge saving from uniform cost search. Now let's see as we go into a harder problems. Okay, now the optimal solution needs 8 steps. Uniform cost search found the optimal solution after expanding more than 6,000 nodes. A star with this heuristic was only or needed only 39. With 12 steps, uniform cost search expanded more than 3 million nodes. Okay, 10 to the power 6 here. 3.6 million nodes. Okay, but A star needed only to expand 227. So as the problem goes harder, of course, the saving in time to find the optimal solution between A star with admissible function, of course, and uniform cost search is increasing. Okay, and this is of course the relaxed problem. As we said, we can move the tile from anywhere to anywhere. For the second heuristic function, which is Manhattan distance, we already said that it is admissible. Now the cost for the start state, you can do it quickly. For every tile, you will find the Manhattan distance between its current position to the correct position. So for example, this 7, and we add all of them, of course. This 7 should be here, so the Manhattan distance will be 1 plus 2, which will be 3 for 7, and then we add for 2, and when we add for 4, and so on. So if you do it, you will find that the cost here is 18. Now let's compare the number of expansions in this case with the previous case. So now we are not comparing, we no longer compare with the uniform cost search, we only compare between the two heuristics. Okay? So the tiles heuristic, which was in the previous slide, and the Manhattan distance, which is in this slide. When we have 4 steps, not much gain using this new heuristic from 13 to 12. 8 steps going from 39 to 25, so a good gain, and much better when the problem gets harder. Okay, so now we have 12 steps. We went from 227 using the first heuristic to 73 only expansion in the second heuristic. So that means that the choice of the heuristic makes a difference. Okay, makes a big difference, and that the second heuristic seems like much faster than the first one. And the reason is the first one was too relaxed. Okay, it's assumed that the cost will be 1 directly for each tile, but the other one was closer to the optimal solution. It was not the optimal solution, of course, but it was closer. Now let me suggest to you a third heuristic, which is the optimal one, which is the actual cost. So if I use the actual cost, let's assume, of course, that we know the actual cost from every step, so we will use it as the heuristic value, as the estimated cost. Would that be admissible or not first? If I use this as a heuristic function, the actual cost, would that be a heuristic an admissible function or not? Or admissible heuristic or not? Any answers? Faisal? Yes, the actual cost, the optimal cost. So every state, we assume that we know the actual cost going from that state to the goal state. And we use that as the heuristic value. Okay, and what is the definition of the admissible heuristic? Equal or more. In this case, it is always equal. So that means it is admissible by definition. Okay, it is admissible by definition. The definition says that the estimated cost has to be, for every state, has to be less than or equal to the actual cost. With this heuristic function, it is always equal to. That's fine. It satisfies the condition, which means that it is admissible. Okay, type. So it is admissible. Type. Would we save on nodes expanded? Of course, we will save a lot because we know where the actual cost, we know the optimal solution, right? So we will save a lot on the nodes that we need to expand. So this heuristic, in terms of expansion here, will be much less. Okay, so it will be even better than Manhattan distance. If that's the case, why don't we use it? What's wrong with it? Yusuf? It's very hard. Yes, first we don't know it, okay? And even if we know how to do it, it will take a lot of time. It is hard to compute. It is hard to compute, so it will take a lot of time to compute. So there is actually a trade-off here. As we have an very easy to compute estimate, we will take a bit more time to find the optimal solution. As we move towards the true cost, okay, doing more computations, doing more work per node to compute the estimations, we will find faster in terms of steps of or in terms of expansion the optimal solution, but we will have much more time in computations. Okay, so that's a trade-off that we need to understand. Being simple will take more steps, will take more expansions. Being very complicated, trying to get very close to the actual cost, will need a lot of computations and thus a lot of running time. So maybe the sweet spot is somewhere in between. So as heuristics get closer to the true cost, you will expand fewer nodes. So you spend less time in expansion of nodes, but usually do more work per node to compute the heuristic itself. Okay, and that's where the trade-off is. Do you have any questions before we leave? I think we should stop here, inshallah, and continue next time. Any questions before we stop? So I hope that our discussion today about heuristics and admissible heuristics will make it easy for us, inshallah, in finding good heuristic functions. Think about relaxing the problem, and in the relaxed problem, you will find an optimal solution easily, and thus this will be an admissible function for the original problem. And you will see that in the project very soon. Okay? Thank you very much. Inshallah, talk to you on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.